Okay, in this lesson we are going to learn about conditional probability. We already talked the other day about how to find the union or intersection of two probabilities doing our and or statements. And we talked about when you're doing the probability of two events both occurring, so that would be our and statement. If the events are independent, then we just multiply their individual probabilities. If the events are dependent, then we figure out what the first probability is, and then we figure out the second probability given that the first one happened. And what we're going to do today is we're going to take a look at this exact same equation that we see here, and we're just going to go ahead and we're going to rearrange it for the conditional probability statement. And if you look down here, you'll notice that those are the exact same equation. The only difference is that I divided the probability of A on the bottom. Now, one tip that I often say is when you're trying to determine how to set this up, the probability, the event that is after the bar, so in this case that would be probability of A, needs to go under the bar. So when you're trying to tell what probability needs to go on the bottom of your fraction, you simply look at what value is after the given that bar, and that is the same value that will go on the denominator. Another thing that we talked about is that with and or statements, order does not matter. So for example, probability of A and B is the same as the probability of B and A. That is also true for or statements. Probability of A or B equals probability of B or A. However, the same is not true for conditional probability. So when we're working with conditional probability, if I had the probability of A given B already happened, that is not going to be the same as the probability of B given A occurred. All right, let's go ahead and take a look at these problems below. So in these cases, what we want to do is we have some information about three events, X, Y, Z, and we need to determine all of these probabilities. I feel like these problems are harder because we don't have any context to put them in. We have no idea what they are, we can't draw a picture, we have no sample space to visualize, we simply have to rely on our formulas. Alright, so for our first one, I'm looking at the probability of X given Z. And for this, we're going to use the formula that we just learned. We are going to say this is equal to the probability of X and Z divided by the probability of Z. Again, using that rule that the probability after the bar is the same as the probability under the bar. From here, we can go ahead and plug in our values. So X and Z is listed right here as 1/3. And when we divide that by probability of Z 2/3, we get 1/2 for our answer. All right, so now let's take a look at the next one, probability of Y given X. Similar idea, we're going to start with their and statement on top, divided by the individual probability of X. And when we look at our answer choices, we don't have probability of Y and X, but we do have probability of X and Y, and those are the same thing. So we're going to say 1/6 divided by probability of X, 1/2, and when we divide those two, we get 1/3. All right, when we step over here into probability of X or Y, we want to use the formula that we talked about for union. So we're going to do probability of X plus probability of Y minus probability of X and Y. Okay, so if we plug in these values, we are going to have 1/2 plus 1/4 minus 1/6, and this gives us 7/12. All right, lastly, we are asked to find probability of Z and Y. Now, if we think about this, right now we have no idea if Z and Y are independent or dependent events. So one of the things that we talked about in class is that if you are unsure, you always assume dependent. When in doubt, assume dependent, and that way you don't make a poor assumption. Okay, so if that's the case, then we know that this and statement is going to be equal to the probability of Z times the probability of Y given Z occurred. However, we don't see that probability up here. So because we know that and statements are reversible, the probability of Y and Z would be the same thing, we can also think about this in another way. We can say, well, what if Y happened first? Then I would find the probability of Z given y occurred. And that I do have. So now I go ahead and I plug in my values, and I have 1/4 times 3/4, and we get 3/16. Okay, there's 2 follow-up questions below here talking about the probability of z knowing that y happens. Well, if we analyze up here, the probability of z is 2/3, and the probability of z given y is 3/4. Well, what this tells me is that if I know y has happened, then z is more likely to occur, because its probability goes from 2/3 to becoming 3/4. So what we can say is that z is dependent on y. The likelihood of z occurring increases if y occurs. And our last question here is whether or not x and y are independent. So to answer this question, we want to think about what it means for events to be independent. If they were independent, then we know that the probability of x and y would equal probability of x times probability of y. So let's check based on what we know. Above in our information, we have that the probability of x and y is 1/6, and we know probability of x is 1/2, and probability of y is 1/4. And those are clearly not equal. So since they are not equal, then this means that x and y are dependent events. All right, let's go on to page 2. So down here on page 2, we have this scenario with a lot of animals. And in this case, what I would recommend that you do is make a chart to help analyze all of our information. So we have cats, dogs, and ferrets, and they are colored black, white, and brown. So what we're going to do is make a chart, and on this chart, we will go ahead and take care of the 3 different options each way. So first we talk about cats, we have dogs, and we have ferrets. And then our colors, we have black, we have white, and we have brown. Okay, so there's 3 black cats, 6 white cats, and 1 brown cat. Okay, so now that we finished our chart, we can go ahead and answer our question. We always want to start by writing the question in words with symbols. So this first problem says the probability that we're dealing with a cat given that this animal is brown. So based on my definition, I'm going to do my and statement on top. I'm going to divide that by the probability of the animal being brown. So if we add up all our animals, we will see that we have a total of 30 animals. So the probability that is a cat and brown, there's only 1 brown cat. So that likelihood is 1 out of 30. The likelihood that we're dealing with a brown animal, well, in this case there are 11 animals that are brown, so we would say 11 out of 30. And if we divide these, we will get 1 out of 11. Now, one thing that we talked about in class is that we can also go ahead and use our chart as more of a visual. So in that case, we can say, all right, I know that I'm trying to find the probability it's a cat. I know I'm dealing with a brown animal. So what we can do is we can focus on the brown column where there are 11 animals, and we can say, all right, out of those 11 animals, what is the likelihood I have a cat? And there's only 1 cat. And that is how we can also think of getting our answer of 1 out of 11. All right, if we look at our next problem, we want to write it in words. Probability this animal is white, given that it is a ferret. So we're going to do the probability that it is a white and a ferret divided by the probability that the animal is a ferret. So just like we did on the previous problem, we can go ahead and we can set up our different equations. So a white ferret, there is only 4 white ferrets, so 4 out of 30. Probability that it's a ferret in general, we have a total of 7 ferrets, so 7 out of 30. And if we divide those, we get 4 out of 7. Using a similar visual model, we can look at this and we can say, all right, I know I'm working with a ferret. So someone says, what's the probability this animal is white if I know it's a ferret? So in that case, I've taken all my animals and restricted them down to only ferrets. So I only have 7 animals to work with. Of those 7 animals, how many are white? And that is how we can also get 4 out of 7s. Pause the video and try the next 2 on your own. Okay, for these last 2 problems, our answers are 5 over 13 and 13 over 17. Now, if you prefer the visual method, solving for part C, probability that it is not a brown dog, given that we know it's a dog, you would focus on the dog row, which gives me 13 options, and then we would find all the ways that we could not be brown, which would be 2 and 3. If we wanted to go ahead and take a look at this last option, all the ways that we are not a cat and not white, given that we are not white. So if we know that our cat is not white, then we know that we are not looking at this row, or that column rather. So we're just looking at the 2 end columns. And then within that, we want to look for all the ways that we could not be a cat. And so that would give me multiple options here. I would have the 2, I would have the 8, I would have the 1 and the 2, and that's how we end up getting 13 out of 17. All right, go ahead and try the remaining options on your own and then unpause the video and check your work. In this scenario, it's easiest to first write out our sample space, which I've done here, and then once we have that, we take the problem and write it in words. Once it's in words, we can go ahead and look to see how many fit that criteria. So for example, on the first problem, we want at least 2 tails and the second coin is a tail. So look through all of your examples and find where the second coin is a tail and there are at least 2 tails. There are 3 options that make that true, which is how I get 3/8. On the next one, I want to know if the second coin is a tail. So look at all of these that I already circled, and there's also one other one that I did not circle because there weren't at least 2 tails. So there are 4 options that have a second coin of tails. So out of those 4 options that have a second coin of tails, 3 of them happen to have 2 tails. And so that's how I get my answer of 3/4. Okay, in our last examples, we have a lot of words going on here, different things that can trick us. What we want to do is pick out the important parts. So we want to know the probability that this person can do a handstand if we know, which means given, they can do a cartwheel. So we start off with our order. Probability of handstand given cartwheel means handstand and cartwheel divided by whatever is after the bar goes under the bar, probability of a cartwheel. And from here, we just pluck those values out of the problem and we divide to get our answer. When we look at the next one here, we have the carnival in town. Again, we're kind of trying to trick you here. The probability that you get sick, given that you ride the tilt-a-whirl 5 times, is 0.84. Ignore all of this stuff about riding it 5 times. 0.84 is what you need to know. Probability of you riding the tilt-a-whirl 5 times is 0.32. What is the probability that you ride the tilt-a-whirl 5 times and get sick? So in this case, we're trying to solve an and problem. So we look at the probability of a tilt-a-whirl times this probability that you get sick given that you rode the tilt-a-whirl. Since these are dependent events, that's why we have to do the probability you get sick given that the tilt-a-whirl already happened. And now we just plug in our decimals and we get 0.27. All right, that's it. Homework is worksheet 7.